All right, so we're back looking at our kinematics of our rotational motion, okay? So we were looking at these equations and I just wanted you to take note of their relation with our translational motion, okay? Which is our normal, x, y motion that we looked at previously, okay? So one thing to note between these two that's not listed here is that if we want to know some kind of distance and we want to relate it to our rotational motion, it's going to equal our radius times our theta or angle. Okay, so this is when you're looking at a circle, okay, and you want to know that arc length, okay? So you'll take your radius and you'll multiply it by your theta here, okay? So that's just something else to note. It's in your textbook briefly, and it's going to be in our example here in a minute, so I wanted to remind you of this or mention it, okay? So let's go ahead and go back to our example here, okay? So remember we were looking at a fishing reel, and we are now on part C, okay? So part C asks, how many revolutions does the reel make, okay, in this time? So let's go ahead and scroll down a little bit. I don't know how to get that to go away. Oh, I'm not trying to do that. Okay. Struggle is real with this. Okay, so part C, we want to know the revolutions that this makes. So we're looking for some kind of angle, okay? So remember that one revolution, I'm just going to put this randomly right here. One revolution is equal to 2 pi radians, okay? So we looked at that in the last problem. So we need some kind of equation to relate our radians to something else that we have. So let's go ahead and look at our kinematic equations, okay? So we have these two equations that we could use. This one, we have our time. This would be 0 for us, our omega naught. We started with 0 meters per second, or radians per second, our velocity. And we do have some alpha, okay? And this one, let's see, we may have that one, but I think this one would be a good one to choose. So let's go ahead and use this one. So we have theta, equals omega naught times t plus 1/2 alpha t squared. Okay. So we have our omega naught is 0. So we can go ahead and plug that in there. And then can go ahead and plug in our alpha, which is 110 radians per second squared, times our time squared, which is 2 seconds. Okay, so if you go 1/2 times 110 times 2 squared, that will give you 220 radians per, or I'm sorry, just radians, right? Because our seconds cross out here. Okay, so if we want to put that into revolutions, okay, we can go ahead and take that 220 radians, it's a 0, sorry, and multiply it by 1 revolution over 2 pi radians, Okay, so go ahead and divide that. Oops. And you get 35.0 revolutions. Okay, so over this time, this has gone through 35 revolutions. Okay. Okay. So let's go ahead and do that. Now we want to know part D, how many meters of fishing line come off the reel during this time. Okay, so that's where that equation that I just talked about will come in handy. So my distance or meters, okay, the length is going to be equal to my radius times the theta, or my radians, okay? So we can go ahead and put in our radius here, 0.045 meters, and that's going to be multiplied by our number of radians, which is going to be 220 radians. So this is going to tell us the distance, okay, that 220 radians will travel over that radius. So let's see, 220 times 0.045, that is going to give me 9.9 meters. Okay. So here is how far my fishing line will go, is almost 10 meters. Oops. Okay. All right, so let's go ahead on to the next problem. Okay, so this problem states, let us consider what happens if the fisherman applies a brake to the spinning reel, achieving an angular acceleration of negative 300, is that what it says? 300 radians per second squared. Okay. Oops. So our acceleration, our angular acceleration, is going to be negative 300 radians per second squared. And it asks how long does it take the reel to come to a stop. So we're looking for some kind of time. Okay. So let's look at our kinematic equations and see what we have or don't have. Okay. So we're looking for time, so we have to be in one of these three equations. And let's see what we have. We have an acceleration, so that would be these two. Okay. And we have that is 0. I'm not sure about our theta. We have this starting value, I'm sorry, our final value here. So I would assume that's what we would need to use. So let's see. So if we go ahead and write this equation out, omega equals omega naught, is it plus? Yeah, plus alpha t. Okay. We know that we are starting from our last problem. So remember our last problem, we had our omega was, I think, yeah, 220 radians per second. Okay, so in this case, that's where we would be starting. So that would be our omega naught. And our final omega, our final velocity, would be 0 because we're going to a stop, right? So this should be 0. So using this equation, we can go ahead and rewrite it to get alpha t equals omega minus omega naught, or t equals omega minus omega naught over alpha. Okay, so we can go ahead and plug our values in. We have 0 radians per second minus 220 radians per second divided by our alpha, negative 300 radians per second squared. And so we have 220 over 300, which gives us 0.733 seconds. So this is the amount of time for the reel to come to a stop. Okay? All right. So let's see. This is going to be our next problem. Okay, and it may be a little bit similar to what we've done. So let's see. A large freight train accelerates very slowly. Suppose one such train accelerates from rest, giving its radius of 0.35 wheels, an angular acceleration alpha 0.25 radians per second squared. After the wheels have made 200 revolutions, so I'm going to say theta is 200 revolutions, how far has the train moved? Okay, well, remember from our last problem, we said that our distance is going to be r times theta. Okay. And remember that theta, we will need to convert since it's in revolutions. So keep that in mind. So we have 0.35 meters times 200 revolutions, but there is 2 pi radians per revolution. Okay. So then go ahead and calculate that, 0.35 times 200 times 2 pi. This means that the train has moved 400 and about 40 meters down the track. Okay. The last question asks, what are the final angular velocity of the wheels and the linear velocity of the train? Okay, so angular velocity is going to be, we had this equation, but we don't know a time, right? No, we do not know a time. So angular velocity, okay, we're running out of time on this video, so we will come back to this problem next time.